Tonight, we're going to talk about a spacecraft that traveled farther than anything humans had ever built, sent back signals from a place no probe had ever been, and then went silent in a way that left engineers staring at their screens for hours, refusing to believe what they were seeing. In January 2003, the last whisper from Pioneer 10 reached Earth from somewhere beyond the orbit of Pluto, more than 7 billion miles away. The signal was so faint, so impossibly thin, that it took the most sensitive antennas on the planet just to pick it out from the background noise of the universe itself. And then nothing. No farewell transmission, no final message, just silence stretching across the void. But the silence wasn't the strange part. Every spacecraft eventually goes quiet. Batteries die, antennas drift out of alignment, components fail in the brutal cold of deep space. What made Pioneer 10's silence different, what made it haunt the engineers and physicists who had spent decades following its journey, was what the spacecraft had been telling us in the years before it went dark. Something out there at the edge of the solar system was pulling on it. Something invisible. Something that didn't appear in any of our equations, didn't match any of our predictions, didn't fit into the comfortable framework of physics that humans had spent centuries building. Pioneer 10 was slowing down, and nobody could figure out why. For more than 30 years, this little spacecraft, a probe smaller than a compact car, weighing less than 570 pounds, sent back data that quietly broke the laws of motion as we understood them. The numbers were small, almost laughably small, a deceleration of about 8 times 10 to the minus 10 meters per second squared. To put that in perspective, it would take a car experiencing that kind of slowdown nearly 30 years to lose 1 mile per hour. It's an effect so tiny that for years, mission controllers assumed it had to be a measurement error, a glitch in the tracking software, some boring instrumental quirk that would eventually be explained away by a tired engineer who finally noticed where a decimal point had wandered. Except it wasn't a glitch. It didn't go away when they checked the equipment. It didn't disappear when they switched to different antennas. It didn't vanish when they used completely independent tracking methods. And when scientists looked at Pioneer 11, Pioneer 10's twin sister probe heading in the opposite direction, on the other side of the solar system, they saw the exact same thing. Two spacecraft, traveling in opposite directions, through different parts of the outer solar system, both being tugged backward by something we couldn't see, couldn't measure directly, and couldn't explain. By the end of tonight, you're going to understand what those two little probes detected at the edge of human exploration, why the discovery sent the entire physics community into a quiet panic that lasted for nearly 2 decades, and what it might mean that the spacecraft carrying humanity's first message to the stars was being slowed down by something that shouldn't exist. Before we get started, if you love stories about the strange and the unexplained out there in the dark between the stars, take a moment to like the video or subscribe. It's a small gesture that genuinely helps this channel reach more curious minds like yours. Now, let's begin. Because the story of Pioneer 10 isn't really a story about a spacecraft. It's a story about everything we thought we knew and everything we still don't. Pioneer 10 wasn't supposed to be famous. When it launched from Cape Canaveral on March 2, 1972, it was a quiet little machine with a quiet little mission. Built by TRW Systems and managed by NASA's Ames Research Center, it was a relatively simple probe with a single primary objective. It was supposed to be the first spacecraft to cross the asteroid belt and survive. That was it. That was the whole job description. Just get through the asteroid belt without being torn apart by debris, and prove that future missions could safely make the journey to the outer planets. Anything beyond that, anything it managed to accomplish after threading the needle through that field of rocks and dust, was considered a bonus. The engineers didn't expect much of a bonus. They gave Pioneer 10 a planned operational lifetime of just 21 months. That was enough time to reach Jupiter, take some photographs, gather some data on the gas giant's radiation environment, and then quietly drift off into the dark, becoming a piece of space junk that would orbit the sun forever, ignored and forgotten. The probe carried only 11 scientific instruments, mostly designed to study charged particles, magnetic fields, and cosmic rays. It had no high-resolution cameras by modern standards. Its imaging photopolarimeter could only produce simple images one strip at a time, slowly building up pictures as the spacecraft rotated. By any reasonable measure, it was a humble little machine, expected to do humble little work. But Pioneer 10 had other plans. It survived the asteroid belt. It reached Jupiter in December 1973, becoming the first object made by human hands to ever see the largest planet in our solar system up close. It sent back the first detailed images of Jupiter's swirling cloud bands, the first measurements of its monstrous magnetic field, and the first hints of just how violent and radiation-soaked that part of the solar system really was. The Jupiter encounter gave Pioneer 10 a gravitational kick, a slingshot boost that sent it hurtling outward on an escape trajectory, faster than any object had ever traveled before. It was now destined to leave the solar system entirely, the first man-made object on a one-way ticket to the stars. And it kept going, long after its planned mission ended, long after the engineers expected its instruments to fail, long after the radioisotope thermoelectric generators that powered it should have decayed below useful levels. Year after year, Pioneer 10 kept reporting in, sending back data from places no human eye had ever observed. It crossed the orbit of Saturn. It crossed the orbit of Uranus. It crossed the orbit of Neptune in June 1983, becoming the first spacecraft to travel beyond all the known planets. And still, faithfully, it kept transmitting. But somewhere out there, somewhere in that vast emptiness between the planets, something began happening to it that nobody could explain. The numbers coming back to mission control didn't quite match the numbers the engineers had predicted. The spacecraft's position, tracked with extraordinary precision by the Deep Space Network, was always just slightly off, always closer to the sun than it should have been, always behaving as though some invisible hand were tugging gently, persistently, impossibly backward. The engineers checked their math. They checked it again. And then they began to realize that the strangest discovery of Pioneer 10's mission wasn't going to be something the spacecraft saw with its cameras or its sensors. It was going to be Pioneer 10 itself. To understand how Pioneer 10 came to be, you have to go back to the late 1960s, to a moment when humanity's relationship with space was changing in ways nobody fully understood yet. The Apollo program was at its peak, astronauts were walking on the moon, and the public imagination had been captured by the idea that we were now a spacefaring civilization. But behind the headlines and the heroics, a quieter conversation was happening inside NASA. A conversation about what came next, because the moon, for all its drama and difficulty, was right next door, just 3 days away by rocket. The real frontier, the place where the truly strange things lived, was much, much farther out. The outer solar system, the realm of the giant planets, and in those years, almost nothing was known about it. In 1965, a young engineer at NASA's Jet Propulsion Laboratory named Gary Flandro made a discovery that would reshape decades of planetary exploration. He noticed that in the late 1970s, the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in a particular geometric pattern, a rare configuration that occurred only once every 175 years. With careful planning, a single spacecraft could use the gravity of each planet to fling itself toward the next one, hopping from world to world in a kind of cosmic billiard game. The mission concept that emerged from this realization became known as the Grand Tour, and it captured the imagination of everyone who heard about it. But before any Grand Tour could happen, before humans could send anything past Mars, one enormous obstacle stood in the way. Nobody knew if a spacecraft could survive the asteroid belt. The asteroid belt, that wide donut-shaped region between Mars and Jupiter, was an unknown quantity in the late 1960s. Telescopes had catalogued a few thousand asteroids, but those were just the largest ones. The conventional thinking was that for every visible asteroid, there might be millions or even billions of smaller rocks and dust grains, all whirling around the sun at tremendous speeds. Some scientists feared the belt was a kind of cosmic minefield, dense enough that anything passing through it would be shredded into fragments within hours. Others were more optimistic, suggesting the belt was probably mostly empty space. Nobody knew for certain. And without that knowledge, The entire dream of exploring the outer planets was stuck on a launch pad. Somebody had to go first. Somebody had to find out. That somebody became the Pioneer program. The program had already existed for years, sending small probes to study the Moon and the inner solar system. But in 1969, NASA approved a new generation of Pioneer spacecraft, designated Pioneer F and Pioneer G, that would attempt something unprecedented. They would be the first probes to leave the inner solar system entirely. The contract to build them went to TRW Systems in Redondo Beach, California, where a team of engineers under the supervision of NASA's Ames Research Center got to work on a design that had to do something nobody had ever done before. Build a machine that could survive years of travel through unknown environments, transmit useful data across distances measured in billions of miles, and operate in temperatures and radiation conditions that no human-built object had ever encountered. The constraints were brutal. Solar panels, the standard way of powering spacecraft, were useless that far from the sun. At Jupiter's distance, sunlight is about 27 times weaker than it is at Earth, and beyond Jupiter, it dwindles further into uselessness. So the engineers turned to nuclear power. Pioneer 10 would carry 4 small radioisotope thermoelectric generators, devices that converted heat from decaying plutonium-238 into electricity. They were small, reliable, and would keep producing power for decades. But they were also dangerous to handle, expensive to build, and politically controversial. There were heated debates about whether a launch failure could scatter radioactive material across populated areas. The engineers spent months designing containment systems that could survive any conceivable accident, building a probe that was as much a piece of safety engineering as it was a scientific instrument. The communication system presented its own nightmare. To send signals across the solar system, the spacecraft needed a high-gain antenna, a dish about 9 feet across that had to point directly at Earth no matter where Pioneer 10 was in space. This created an interesting engineering puzzle. The spacecraft would be spinning, rotating on its axis to maintain stability, but the dish had to stay locked on Earth. The solution was elegant in its simplicity. The antenna was mounted on the spin axis itself, so that no matter how the rest of the spacecraft rotated, the dish always faced the same direction. As long as the engineers could keep that spin axis pointed at Earth, communication would work. And the entire mission depended on that simple geometric trick functioning perfectly for years on end, in conditions nobody could predict. Then there was the matter of the message. In the weeks before the launch, journalist and science writer Eric Burgess and astronomer Carl Sagan got together with Cornell University astronomer Frank Drake and proposed something audacious. If Pioneer 10 was going to leave the solar system, if it was going to drift forever between the stars, shouldn't it carry some kind of message? A greeting from humanity to whatever might one day find it. NASA approved the idea, but only barely, and only because it was relatively cheap and easy to implement. Sagan and Drake, working with Sagan's wife Linda Saltzman Sagan, designed a small gold-anodized aluminum plaque, 6 by 9 inches, etched with symbols meant to communicate where the spacecraft came from. There were figures of a man and a woman, a diagram of the solar system with Earth highlighted, and a complex symbolic key based on the radio frequency of hydrogen, a kind of universal physical constant that any technologically advanced civilization would recognize. The plaque was bolted to the antenna support struts, where the chances of micrometeorite erosion were lowest. It would be Pioneer 10's calling card, a message in a bottle thrown into the cosmic ocean. The launch itself happened on a cool spring evening in Florida. On March 2, 1972, at 8:49 p.m. Eastern Time, an Atlas Centaur rocket roared off the pad at Cape Canaveral with Pioneer 10 perched on top. The launch had to be precisely timed to put the spacecraft on a trajectory that would intercept Jupiter 21 months later, which meant the launch window was narrow. Any delay of more than about an hour, and the trajectory would no longer work. Mission controllers held their breath as the rocket climbed into the night sky, separated through its stages flawlessly, and released Pioneer 10 into a trajectory that would carry it across the solar system at unprecedented speed. The probe was moving at over 32,000 miles per hour relative to Earth at the moment of separation, faster than any object humans had ever launched. Within 11 hours, it crossed the orbit of the Moon, a journey that had taken Apollo astronauts 3 days. By the end of its first week, it was already farther from Earth than any planet except Mercury, Venus, and the Moon itself. The little probe was on its way, racing toward an encounter with the largest world in our solar system and toward a mystery that nobody could possibly have anticipated. To understand why what happened next was so deeply unsettling to the people watching Pioneer 10 from Earth, you have to understand just how confident physicists were in the laws that governed its motion. Not arrogant confidence, not the kind that comes from hubris, but a calm, weathered confidence built on 300 years of relentless testing. Because when it came to predicting how an object moved through the solar system, when it came to calculating where a spacecraft would be on a Tuesday afternoon 10 years from now, the equations were considered settled. Done. Finished. There was no scientific question more thoroughly answered than the question of how gravity worked at the scales of planets and probes, or so everyone believed. It started with Isaac Newton in the late 17th century. In 1687, he published the Principia Mathematica, a book that contained, among other revelations, a single equation that would dominate physics for the next 2.5 centuries, the law of universal gravitation. It stated that every object in the universe pulled on every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It was simple, it was elegant, and astonishingly, it worked. Newton's law explained why apples fell from trees and why the Moon orbited Earth and why planets traced elliptical paths around the Sun. It predicted the timing of eclipses, the return of comets, the orbits of moons around distant worlds. For 2 centuries, every test threw at it, the equation passed. Astronomers used it to discover Neptune by analyzing tiny irregularities in the orbit of Uranus, calculating where the unseen planet had to be hiding before they ever pointed a telescope in its direction. It was, by any measure, one of the most successful equations in the history of human thought. Then came Albert Einstein. In 1915, Einstein published his general theory of relativity, which reframed gravity not as a force, but as a curvature of spacetime itself. Massive objects bent the fabric of the universe, and other objects followed the curves. It was a profoundly weirder picture of reality, but it predicted things Newton's equations couldn't, including a small but measurable extra rotation in the orbit of Mercury that Newtonian gravity could never quite account for. Einstein's theory passed every test that came its way too. Light bending around the Sun during a solar eclipse, time slowing down for clocks in strong gravitational fields, the precise timing of binary pulsars, the existence of gravitational waves. By the time Pioneer 10 launched in 1972, general relativity was considered one of the most well-tested theories in all of physics. Between Newton's classical equations for ordinary situations and Einstein's relativistic corrections for extreme ones, scientists had a complete toolkit for predicting how objects moved through the solar system. And the predictions weren't just close. They were extraordinarily, mind-bogglingly precise. Consider what NASA was actually doing when it tracked Pioneer 10. The spacecraft was equipped with a radio transponder, a device that received signals from Earth and sent identical signals back. By measuring the exact time it took for a signal to travel to the spacecraft and return, mission controllers could calculate the distance to Pioneer 10 with extraordinary accuracy. By measuring the frequency shift in the returning signal, the Doppler effect caused by the spacecraft's motion either toward or away from Earth, they could determine its velocity along the line of sight to within fractions of a millimeter per second. These measurements were made using the Deep Space Network, an array of giant radio antennas spread across 3 sites around the world. One in Goldstone, California, one near Madrid, Spain, and one outside Canberra, Australia. The 3 sites were positioned so that as Earth rotated, at least one of them was always able to see the spacecraft, providing continuous communication coverage. The antennas themselves were marvels of precision engineering. The largest were 230 feet across, weighing thousands of tons, capable of detecting signals so faint that the entire power output of Pioneer 10's transmitter, by the time it reached Earth, was measured in trillionths of a watt. A modern cell phone broadcasts more energy in a single second than Pioneer 10's signals delivered to Earth over an entire year. And yet the Deep Space Network could pull those whispers out of the cosmic background noise, decode them, and extract precise information about where the spacecraft was and how fast it was moving. The accuracy was almost unreasonable. By combining months and years of tracking data, navigators could pinpoint a spacecraft's position to within a few hundred meters, even at distances of billions of miles. That's like being able to spot a soccer ball on the surface of the moon from your backyard. With this level of precision, predicting where Pioneer 10 would be at any given moment became an exercise in applied physics. The navigators would input the known positions and masses of every significant body in the solar system: the Sun, the planets, the major moons, even some of the larger asteroids. They would account for the gravitational tugs each of these objects exerted on the spacecraft. They would add in the small but measurable effects of general relativity, including the way the curvature of spacetime near the Sun bent the spacecraft's trajectory slightly. They would include the gentle pressure of sunlight itself, which pushed on the spacecraft with a force so small it would take days to accelerate a feather. Every conceivable influence was modeled, calculated, and folded into the trajectory predictions. And then they would compare those predictions to the actual measurements coming back from the spacecraft. The match was supposed to be perfect. For most of human history, this kind of confidence in mathematical prediction would have seemed delusional. Ancient astronomers tracking the planets watched them wander unpredictably through the sky, sometimes moving forward, sometimes backward, defying every attempt to find a pattern. It took Johannes Kepler years of obsessive analysis of Tycho Brahe's observations to realize that planets moved in ellipses rather than perfect circles, a discovery that overturned 2,000 years of astronomical assumption. Even after Kepler, even after Newton, there were always small discrepancies between prediction and observation. Most of them turned out to be minor errors in the input data: an imprecise mass estimate for a moon, an asteroid whose orbit hadn't been carefully measured, a small computational mistake. As measurements improved and computing power grew, those discrepancies disappeared. By the 1970s, when Pioneer 10 was launched, celestial mechanics had reached a level of accuracy where any unexplained deviation from prediction was assumed to be a measurement error rather than a flaw in the underlying physics. This was the world Pioneer 10 was launched into. A world where the equations were trusted, where the trajectory was knowable, where the spacecraft's position years into the future could be predicted with breathtaking precision. The navigators at NASA's Jet Propulsion Laboratory expected Pioneer 10 to do what every other spacecraft had done. They expected it to follow the path their equations laid out for it. They expected the actual measurements and the predicted positions to match, give or take a tiny rounding error that would gradually shrink as their analysis techniques improved. They expected, in short, that the universe would behave the way it was supposed to behave. Pioneer 10 was about to teach them that the universe sometimes has other ideas. The first hint that something was wrong with Pioneer 10's trajectory didn't arrive with a dramatic announcement or a flash of insight. It arrived quietly, almost embarrassingly, buried in the routine data analysis that mission navigators performed every few weeks. The man who first noticed it was named John Anderson, a soft-spoken physicist working at NASA's Jet Propulsion Laboratory in Pasadena, California. By the time he started looking carefully at the numbers, in the early 1980s, Pioneer 10 had already been in space for nearly a decade. It had passed Jupiter, crossed the orbits of Saturn and Uranus, and was now hurtling outward through a region of the solar system where the gravitational influences were small, the sunlight was dim, and the trajectory should have been almost laughably simple to predict. Anderson wasn't actually looking for anomalies when he stumbled across one. He had a different goal entirely. He was using the precise tracking data from Pioneer 10 and its twin sister, Pioneer 11, to test a hypothesis about gravity, an idea proposed by some theorists that the gravitational constant might vary slightly over very long distances, or that there might be tiny deviations from Newton's law at scales beyond the orbits of the planets. To do that kind of test, he needed extraordinary precision. He needed to know exactly where each spacecraft was, exactly how fast it was moving, and exactly how those numbers compared to the predictions of standard physics. So he pulled together years of Doppler tracking data, fed it through the most accurate models available, and waited to see what came out the other side. What came out the other side made him stop and frown at his computer screen. The two spacecraft weren't quite where they were supposed to be, both of them. Pioneer 10 traveling in one direction, Pioneer 11 traveling in roughly the opposite direction, on entirely separate trajectories, were each drifting from the predictions by a small but consistent amount. They were arriving at their measured positions slightly closer to the sun than the equations said they should be. Not by much. The discrepancy was so small that for years nobody had bothered to investigate it. But it was there, and it wasn't going away. Anderson's first reaction was the same reaction that anyone with 3 decades of experience in spacecraft navigation would have. It had to be a mistake. There were 1,000 things that could create a small systematic error in tracking data, and almost all of them had to do with the spacecraft itself rather than with anything happening in the cosmos. Maybe there was a slow leak from one of the thrusters, releasing a tiny puff of gas that produced a continuous, gentle thrust in one direction. Maybe the calibration of the radio transponder had drifted over time, causing the Doppler measurements to be slightly off. Maybe one of the constants in the trajectory model needed updating, a moon's mass that had been imprecisely estimated decades ago, or an asteroid's gravity that hadn't been properly accounted for. So he started checking. Methodically, one possibility at a time, the thruster hypothesis was the first to be examined. Spacecraft like Pioneer 10 carried small reaction control jets that fired occasionally to keep the high-gain antenna pointed at Earth. Each firing produced a small, brief impulse. If something was wrong with the valves, if a small amount of gas was escaping continuously rather than being released only during planned maneuvers, that could produce exactly the kind of slow, persistent acceleration that the data was showing. Anderson and his colleagues went through the spacecraft's engineering logs, looking for evidence of any unaccounted-for gas releases. They didn't find any. The thrusters had been firing exactly when they were supposed to, in exactly the durations they were supposed to, and the cumulative effect of those firings had already been included in the trajectory model. Whatever was pushing on Pioneer 10, it wasn't coming from inside the spacecraft. At least, not from any source the engineers could identify. Then they looked at the radio system. The Doppler tracking technique that NASA used relied on precise frequency measurements, and any drift in the spacecraft's onboard reference oscillator could create systematic errors in the apparent velocity readings. Anderson and his team spent months analyzing the calibration data, comparing the frequencies the spacecraft was transmitting to the frequencies being received on the ground, checking every possible source of measurement error. The radio system was working exactly as designed. The Doppler shifts being measured were real. The spacecraft really was drifting from its predicted path. When the spacecraft itself couldn't be blamed, attention turned to the trajectory model. Maybe the problem was with the way the gravity of various solar system bodies was being calculated. The team painstakingly went through every input, updating the masses of moons that had been refined by subsequent missions, including new measurements of asteroid positions from improved telescopic surveys, even accounting for tiny gravitational influences from objects that had previously been ignored as too small to matter. The corrections made the predictions slightly more accurate in some cases, but they didn't make the anomaly go away. The Pioneer probes were still arriving in positions that were measurably different from where the equations said they should be. By the late 1980s, the discrepancy had stopped looking like a measurement error and had started looking like something else, something more uncomfortable. Anderson found himself returning to the data over and over, hopping each time to find the simple explanation that would resolve the mystery. He didn't find it. Instead, each new analysis confirmed what the previous ones had shown. There was an extra, unaccounted-for acceleration acting on Pioneer 10 and Pioneer 11. It was small, around 8 billionths of a meter per second squared, a number so tiny it seemed almost meaningless. But it was real, it was consistent, and it pointed in a very specific direction, toward the sun. That direction was the thing that troubled Anderson the most. If the anomaly had been pointing in a random direction or varying over time, it would have been easier to dismiss as some kind of instrumental noise. But the fact that both spacecraft seemed to be experiencing a gentle pull back toward the inner solar system, even though they were on completely different trajectories, heading in completely different directions, suggested that whatever was happening, it had something to do with the sun, or with distance from the sun, or with something in the geometry of the solar system that nobody had thought to include in the equations. He hesitated to publish anything. The result was too strange, too easily mistaken for an error, too likely to make him look foolish in front of his colleagues. For years he kept refining the analysis, accumulating more data, hoping that one of the next batches of measurements would show the anomaly slowly fading away as some hidden systematic effect was finally identified and corrected. It never did. As the 1990s began and Pioneer 10 continued its lonely outbound journey, the discrepancy stubbornly remained. The little spacecraft, almost 20 years out from Earth now, was still being tugged backward by something that wasn't supposed to exist. And John Anderson was beginning to suspect that he was looking at the first crack in a wall that physicists had spent 3 centuries believing was solid. By the early 1990s, John Anderson had grown convinced that he needed help. The anomaly in Pioneer 10's trajectory wasn't going to be solved by one physicist quietly running calculations in his office. If it was real, if it was something more than a hidden bug in the analysis software, then proving it would require an entire toolkit of independent methods, alternative software pipelines, and skeptical collaborators who would tear his work apart looking for mistakes. That's how science actually progresses when something genuinely strange shows up in the data. You don't trust your own conclusions. You hand them to someone who would love nothing more than to prove you wrong, and you wait to see if they can. The first major collaborator to join the investigation was a Russian-born physicist named Slava Tarashev, who had come to JPL from the Russian Academy of Sciences after the collapse of the Soviet Union. Tarashev had a background in theoretical physics, in the kind of precise mathematics that general relativity demanded, and he brought a fresh set of eyes to the problem. He didn't trust Anderson's results, not because he doubted Anderson personally, but because that's the right scientific instinct when someone tells you the laws of motion might be wrong. Tarashev pulled the raw tracking data himself, ran it through entirely independent software, made his own assumptions about which corrections to apply, and waited to see what the numbers said. They said the same thing Anderson's numbers had been saying for nearly a decade. The pioneers were being decelerated by something that wasn't in the equations. To understand how they could be so sure, you have to appreciate what Doppler tracking actually looks like at the level of raw measurement. When the Deep Space Network sent a radio signal to Pioneer 10, that signal traveled at the speed of light, took hours to reach the spacecraft, and was received by the onboard transponder. The transponder then generated a new signal at a precisely defined frequency ratio relative to the incoming one, 240 divided by 221, a strange-looking fraction chosen for very specific engineering reasons, and beamed that signal back to Earth. By comparing the frequency of the outgoing signal to the frequency of the returning signal, the navigators could calculate exactly how fast the spacecraft was moving along the line of sight. The math was identical to the way a radar gun measures the speed of a passing car, except the cars were billions of miles away, and the precision required was thousands of times tighter. The actual frequency measurements were made using hydrogen masers, atomic clocks of such extraordinary stability that they would drift by less than a second over millions of years. These masers were the heartbeat of the entire tracking operation. They defined what a second was, what a frequency was, what the standard against which all measurements were compared. Without them, none of the precision of the Deep Space Network would be possible. With them, mission controllers could measure velocity changes as small as fractions of a millimeter per second, which is roughly the speed at which a snail moves divided by 1,000. That's the scale at which they were chasing the Pioneer anomaly. Snail's pace divided by 1,000, persisting consistently for decades, across two different spacecraft, on opposite sides of the solar system. But raw tracking data was only the beginning. Turning those Doppler measurements into a trajectory required massive amounts of computation, and the computational tools themselves became part of the story. JPL had developed a software package called the Orbit Determination Program, or ODP, that handled most of NASA's deep space navigation. It was a complex piece of code with roots going back to the 1960s, written and rewritten by generations of engineers, and it incorporated every known physical effect that might influence a spacecraft's motion. Solar gravity, planetary perturbations, general relativistic corrections, solar radiation pressure, even the tiny gravitational influence of distant Pluto. Running the ODP on years of tracking data produced trajectory solutions that were considered the gold standard of spacecraft navigation. And running it on the Pioneer data produced the same anomalous result every time. To verify that the anomaly wasn't an artifact of the ODP itself, Turyshev and his colleagues began searching for independent software that could analyze the same data without making the same assumptions. They found a partner in the Aerospace Corporation, a federally funded research center that maintained its own trajectory analysis tools. The aerospace team ran the Pioneer data through their software, called CHASMP, which had been developed entirely independently of JPL's code. The two programs shared no common subroutines, no common assumptions, no shared history. They were as independent as two pieces of software analyzing the same problem could possibly be. And they produced almost identical results. The anomaly was there in both. Whatever was happening to Pioneer 10 and Pioneer 11, it wasn't a bug in any particular piece of code. It was something in the data itself. The team then turned to another verification technique called ranging. While Doppler measurements told you how fast a spacecraft was moving, ranging measurements told you exactly how far away it was. By transmitting a precisely timed signal and measuring the exact moment the response came back, mission controllers could calculate the distance to Pioneer 10 to within meters. These range measurements were taken alongside the Doppler data, and they provided an independent check on the trajectory. If the spacecraft was being decelerated by some unknown force, the ranging data should show it just as clearly as the Doppler data. And it did. The ranging measurements confirmed that Pioneer 10 was closer to the Sun than the standard trajectory predicted, by exactly the amount that the Doppler-derived acceleration would produce. Two independent measurement techniques, agreeing perfectly with each other and disagreeing with the predictions of standard physics. There was one more layer of verification that the team built into the investigation. They needed to make sure the anomaly wasn't somehow coming from Earth itself, from some quirk in the Deep Space Network or in the Earth's rotation models that might be subtly biasing all the measurements. So they analyzed data from each of the three DSN sites separately. Goldstone in California, Madrid in Spain, and Canberra in Australia. If the anomaly was an artifact of a particular antenna or a particular geographic location, it should look different from each site. It didn't. Every tracking station saw the same effect, the same magnitude, the same direction. The anomaly was riding along with Pioneer 10 as it moved through space, not appearing in the equipment that was measuring it. By the time the team was ready to publish their findings, the anomaly had been verified by independent investigators using independent software, analyzing independent data streams from independent tracking facilities. Every conceivable source of measurement error had been examined and ruled out. The methodology was watertight. The tools were unimpeachable. The data was clean, which meant that whatever they were going to write up and submit to the scientific community wasn't going to be an easy paper to dismiss. It was going to be a paper that said, very politely, that something out there was doing something we couldn't explain. And in 1998, after more than 15 years of careful, patient, paranoid investigation, the paper was finally ready to be sent to the world. The paper that finally appeared in the journal Physical Review Letters in 1998 carried a title designed to be as cautious as possible. It read, in full, "Indication from Pioneer 1011, Galileo and Ulysses data of an apparent anomalous, weak, long-range acceleration." Every word in that title had been chosen carefully. Indication, not proof. Apparent, not real. Anomalous, leaving open the possibility that some hidden source might still be discovered. The authors, Anderson, Lang, Lau, Liu, Nyato, and Turyshev, knew exactly what they were doing. They were dropping a stone into a very still pond, and they wanted to make sure that everyone understood they weren't claiming to have overturned 3 centuries of physics. They were just reporting what they had measured. The interpretation, the meaning of it, was somebody else's problem. That somebody else turned out to be the entire physics community. Within weeks of publication, the paper was being passed around like contraband at universities and research institutes around the world. Theorists who had spent careers refining the standard models of gravity and motion suddenly found themselves staring at a number that seemed to refuse to fit anywhere. An acceleration of 8.74 times 10 to the minus 10 meters per second squared toward the sun, affecting at least 2 spacecraft and possibly more. There was something almost teasing about the smallness of the effect. It was just large enough to be measurable, just persistent enough to be real, and just unexplained enough to be terrifying. If it had been larger, someone would have noticed it decades earlier. If it had been smaller, it could have been buried in the noise and forgotten. Instead, it sat in this awkward middle ground, daring physicists to take it seriously. The first reaction in many physics departments was an unconcealed wave of skepticism. Senior researchers who had spent their careers trusting Newtonian gravity and general relativity didn't want to believe that 2 NASA spacecraft were quietly demonstrating that one of those frameworks needed to be revised. Conference room conversations took on a particular flavor. "Have you heard about the Pioneer thing?" "Yeah, it has to be wrong. It has to be." Anderson and Turyshev were respected, certainly, but respected scientists had been wrong before, and the alternative, that the equations themselves were missing something, was almost too much to contemplate. Some physicists openly predicted that within a year or two, someone would identify a mundane, systematic effect that explained everything, and the anomaly would quietly disappear from the literature. They were happy to wait for that to happen, but the harder people looked at the paper, the more uncomfortable they became, because the authors had clearly anticipated every objection. The paper included long sections methodically addressing potential sources of error. Solar radiation pressure, drag from interplanetary dust, heat radiation from the spacecraft, gas leaks, errors in the planetary ephemerides. The authors had run the numbers on every one of these effects, demonstrated that none of them could plausibly produce an acceleration of the observed magnitude, and concluded that even when you stacked all the conventional explanations together, you still couldn't account for what was happening. The methodology was rigorous in a way that made it hard to wave away. Critics found themselves in the uncomfortable position of needing to either find a specific error nobody else had spotted in 15 years of analysis, or accept that the anomaly was real and start asking what it meant. That second option was where things got genuinely strange. Because as soon as physicists started seriously entertaining the possibility that the Pioneer data was telling them something true, the floodgates opened on possible interpretations. Within a few months of the paper's publication, dozens of theoretical proposals began appearing in physics journals and on preprint servers. Some of them were modest. Maybe there was an exotic form of matter in the outer solar system that hadn't been accounted for. Maybe some property of the solar wind interacted with spacecraft in ways nobody had modeled. Maybe there was a subtle gravitational effect from the sun's oblate shape that had been calculated incorrectly. These were the sober proposals, the ones that tried to fit the anomaly into existing physics with minimal disruption. Then there were the less modest proposals. Theory that had been quietly haunting the edges of physics for almost 2 decades, called modified Newtonian dynamics, or MOND, suddenly found itself in the spotlight. MOND had been developed in 1983 by by an Israeli physicist named Mordechai Milgrom, who had been trying to explain why galaxies seem to rotate faster than their visible mass should allow. Most physicists explained this by invoking dark matter, vast halos of unseen particles holding galaxies together. But Milgrom proposed an alternative. What if gravity itself behaved differently at very low accelerations? What if, below some threshold, Newton's equations needed to be modified? MOND made specific predictions about how this modification would look, and one of those predictions involved an acceleration value remarkably close to the Pioneer anomaly. The coincidence was eerie. Suddenly, a theory that had been considered fringe was being discussed seriously in the most prestigious physics departments in the world. Other theorists went further. Some proposed that the Pioneer anomaly was evidence of a previously unknown gravitational effect related to the expansion of the universe itself, that the same dark energy responsible for accelerating cosmic expansion might be exerting tiny tugs on objects within our solar system. Others suggested it might be a signature of extra dimensions, of gravity leaking out into spatial dimensions we couldn't perceive. A few brave physicists proposed even stranger ideas, including theories involving a slow drift in the speed of light over cosmic time, or modifications to general relativity that introduced new fundamental fields. Most of these proposals were almost certainly wrong, but the fact that serious physicists were taking them seriously enough to publish papers about them said something profound about the state of confusion the Pioneer anomaly had created. The press coverage, when it came, was less measured than the scientific debate. Magazines and newspapers ran stories with headlines suggesting that NASA had discovered a flaw in Einstein's equations, that the laws of physics might need to be rewritten, that the Pioneer spacecraft had stumbled onto something that could revolutionize our understanding of the universe. Some of these headlines were exaggerated. Most physicists, even the ones who took the anomaly seriously, still believed that a conventional explanation would eventually be found. But the underlying excitement was real. For the first time in a long time, an experimental result was challenging the foundations of one of the most successful theories in science. People who hadn't thought about gravity since high school were suddenly reading articles about Pioneer 10 and feeling, perhaps for the first time, that the universe might still have genuine surprises in store. Inside JPL, Anderson and Turyshev watched the response with a mixture of vindication and unease. They had been telling people for years that the anomaly was real, and now everyone was finally listening. But they also knew something the rest of the community was just starting to grasp. The 1998 paper hadn't ended their investigation. It had merely opened a door. Behind that door, the data went deeper, the patterns got stranger, and the questions multiplied faster than anyone could answer them. The discovery that had taken them more than 15 years to publish was only the beginning of what they would eventually find. The strangest thing about the Pioneer anomaly wasn't that it existed. Plenty of strange things existed in physics. The strangest thing was its shape, or more precisely, its lack of one. As Anderson, Turyshev, and a growing team of collaborators continued analyzing the data through the late 1990s and into the early 2000s, they began to notice something about the anomaly that hadn't been emphasized in the original 1998 paper. Something that made the puzzle dramatically harder to solve. The acceleration wasn't getting weaker as the spacecraft traveled outward. It wasn't getting stronger. It wasn't varying in any obvious way at all. It just sat there, a constant gentle tug, year after year after year, regardless of where Pioneer 10 happened to be at the moment. This sounded innocuous, but it was actually devastating to most of the conventional explanations that had been proposed. Almost every force in physics has some kind of distance dependence. Gravity falls off with the square of the distance, so any gravitational explanation involving a hidden mass should produce an effect that grew weaker as the spacecraft moved farther away. Electromagnetic forces also weaken with distance. The pressure from sunlight diminishes as the spacecraft recedes from the sun. Drag from interplanetary dust depends on the local density of dust, which varies with location. Almost any plausible physical mechanism predicts that the strength of the Pioneer anomaly should change as the spacecraft moved through different regions of space. But it didn't. The data showed a flat, featureless line stretching across billions of miles. Wherever Pioneer 10 went, the anomaly went with it, at the same intensity, like a shadow it couldn't shake. That constancy was deeply weird. It meant that the source of the anomaly couldn't be anything localized in the solar system. A massive but unseen object hiding beyond Neptune would have produced an effect that varied as the spacecraft moved closer or farther from it. A region of dense dust would have left a signature as the spacecraft entered and exited the region. Even an undiscovered subtle effect from the sun's gravity should have weakened over the enormous distances the pioneers had traveled. Instead, the anomaly behaved as though it were a property of the spacecraft themselves, or of the deep space environment as a whole, rather than something tied to any particular place. And that opened up some very uncomfortable theoretical possibilities. While the team was wrestling with this, they began folding in data from other spacecraft to see whether the Pioneer effect was unique or whether it pointed to a more general phenomenon. The Galileo probe, which had been launched in 1989 to orbit Jupiter, had spent years in deep space being tracked by the same deep space network. The Ulysses probe, an international mission that had flown over the poles of the Sun, had also accumulated vast amounts of precision tracking data. Both spacecraft were potential test subjects. If the Pioneer anomaly was a real, universal effect, it should show up in their trajectories too. And when Anderson's group pulled the data, the result was both encouraging and confusing in roughly equal measure. Galileo and Ulysses did show small, unexplained accelerations in their tracking data, but the values didn't precisely match the Pioneer numbers. Galileo's anomaly seemed slightly different in magnitude. Ulysses showed an even more complex pattern, partly because of its unusual orbit over the Sun's poles and the difficulty of accounting for solar radiation pressure on such a strangely oriented spacecraft. The team had to be honest about what this meant. The data from these missions was suggestive, but it wasn't a clean confirmation. The Pioneers remained the gold standard because their geometry was simple. They were spinning probes flying outward in roughly straight lines, with their high-gain antennas always pointed at Earth. That simplicity made their tracking data unusually clean. Galileo and Ulysses had more complex spacecraft designs, with three-axis stabilization rather than spin stabilization, and that introduced sources of small accelerations that were much harder to model. The investigators could see that something resembling the Pioneer anomaly might be present in those missions too, but they couldn't isolate it cleanly enough to be sure. The team then did something that would prove enormously consequential. They went looking for older Pioneer data. The 1998 paper had been based primarily on tracking data from after 1987, when the Doppler measurements had become particularly precise. But the spacecraft had been transmitting since 1972. That meant there were 15 years of earlier tracking records sitting on magnetic tapes in archives, much of it never analyzed in detail. If the team could recover that data and reprocess it with modern techniques, they could test whether the anomaly had been present from the beginning or whether it had appeared at some specific point during the mission. The archive search was its own adventure. JPL storage facilities held boxes of original tracking records on agging tape formats that hadn't been read in decades. Some of the tapes had degraded. Some used data formats whose specifications had been lost. Engineers had to rebuild old hardware to even read them. Tarashev and his collaborators spent years digging through this material, slowly recovering data from earlier and earlier phases of Pioneer 10's mission. What they found pushed the anomaly back, further and further, into the spacecraft's history. And then came the most uncomfortable coincidence of all. A coincidence that some physicists found deeply meaningful and others found embarrassingly suggestive. The numerical value of the Pioneer anomaly, that 8.74 times 10 to the minus 10 meters per second squared, turned out to be remarkably close to a fundamental quantity that appeared throughout cosmology. If you multiplied the speed of light by the Hubble constant, the parameter that describes how fast the universe is expanding, you got a number with the same units and almost exactly the same value as the Pioneer anomaly. The two quantities were close enough that the match couldn't be casually dismissed. And it wasn't just a numerical coincidence. There were physical reasons to think the connection might be real. The Hubble constant describes a kind of universal scale for cosmic dynamics. Combining it with the speed of light produced a characteristic acceleration that might naturally appear in any theory connecting local physics to the expansion of spacetime as a whole. Some theorists found this irresistible. If the Pioneer anomaly was somehow tied to the expansion of the universe, that would explain why it was constant across the spacecraft's entire trajectory. The cosmic expansion didn't depend on where you were. It was a property of spacetime itself. A connection between Pioneer 10's tiny deceleration and the largest-scale dynamics of the cosmos would have been one of the most profound discoveries in physics history. Other theorists, more cautious, pointed out that humans had a long history of finding meaningful-looking numerical coincidences that turned out to mean nothing at all. Two numbers being close to each other didn't necessarily mean they were related, but the coincidence haunted the discussion. It refused to go away. And as more data came in, and as more sophisticated analyses confirmed that the anomaly really was constant and really did have a value uncomfortably close to that cosmological scale, the question hung in the air, unanswered. Was Pioneer 10 quietly measuring something about the universe that nobody had ever measured before, from a place no probe had ever been, with an instrument that wasn't even designed to make that measurement? As the new millennium opened and the investigation widened, something began emerging from the data that nobody had been looking for. The Pioneer anomaly wasn't alone. It had cousins. Other spacecraft, in other contexts, were showing their own small mysterious accelerations that nobody could fully explain. The pattern wasn't loud or obvious. You had to be looking carefully to see it. But once you noticed, it was hard to unnotice. And the more cases that came to light, the harder it became to believe that all of them were independent coincidences. Something was going on, possibly something with multiple symptoms, and the Pioneers were just the most visible expression of a problem that ran deeper through our spacecraft, tracking data than anyone had previously realized. The clearest of these cousins came from an unexpected place. When spacecraft swing past Earth on their way to other destinations, they use the planet's gravity as a kind of slingshot, exchanging a tiny amount of Earth's orbital energy for a boost in their own velocity. These maneuvers, called gravity assists, are routine. They are calculated to extraordinary precision and verified by tracking the spacecraft as it approaches and departs the planet. The math is supposed to work out exactly. The spacecraft should come in at a specific velocity, swing around, and leave at a specific different velocity, with the difference determined entirely by well-known orbital mechanics. But in the late 1990s, navigators at JPL began noticing that some flybys weren't matching their predictions. The spacecraft were coming out of their slingshots with velocities slightly different from what the equations said they should have. Sometimes faster, sometimes slower, always by tiny amounts. Always for reasons nobody could pin down. The Galileo probe had shown one of these flyby anomalies during its 1990 swing past Earth, picking up an extra few millimeters per second that nobody could account for. The NEAR Shoemaker spacecraft, on its way to study the asteroid Eros, showed a similar effect during its Earth flyby in 1998. The Cassini probe, headed for Saturn, showed something during its 1999 Earth encounter. The European Rosetta mission, designed to rendezvous with a comet, showed an anomaly during its 2005 Earth flyby that briefly puzzled mission controllers before being filed away as another unexplained quirk. Each of these effects was small. Each was easy to dismiss as a measurement error or some unmodeled feature of the spacecraft. But taken together, they hinted at something more systematic. Multiple spacecraft, in multiple decades, all showing small accelerations during a specific type of maneuver, all in ways that resisted easy explanation. It wasn't the same effect as the Pioneer anomaly. The flyby anomalies were brief, sudden velocity changes rather than persistent slow accelerations. But the fact that both phenomena existed at the same time, in the same general arena of unexplained spacecraft behavior, made some physicists wonder whether they might share a common root cause. While these parallel mysteries were unfolding, Anderson and Turashev's team had been wrestling with another question buried in the Pioneer data itself. A question about direction. They had originally reported that the anomalous acceleration pointed toward the sun. But as the analysis grew more sophisticated, the answer turned out to be less clean than that. The geometry of the situation was inherently confusing. Pioneer 10 was traveling away from the sun, but it was also traveling roughly in the direction of its high-gain antenna, which was always pointed back toward Earth. The sun and Earth, from Pioneer 10's vantage point billions of miles out, were almost in the same direction. The angle between them, as seen from the spacecraft, was very small. That meant that an acceleration pointing toward the sun looked almost identical to an acceleration pointing toward Earth, and almost identical to an acceleration pointing back along the spacecraft's direction of motion, and almost identical to an acceleration pointing along the spin axis. The tracking data couldn't easily distinguish among these possibilities. This was more than a technical detail. It mattered enormously for understanding what the anomaly actually was. If the acceleration pointed precisely toward the sun, that would suggest a gravitational source, something to do with solar mass, or some new field generated by the star. If it pointed toward Earth, that would suggest something about the radio communication itself, perhaps an effect related to the signals traveling between Pioneer 10 and the tracking antennas. If it pointed along the spacecraft's direction of motion, that would suggest some kind of drag from the interplanetary medium. And if it pointed along the spin axis, that would suggest the effect originated somewhere on the spacecraft itself. Each interpretation pointed to a fundamentally different kind of physics, and the data, as good as it was, couldn't yet say which interpretation was correct. The team had to acknowledge that what they had been describing as a sunward acceleration could just as easily be something else, something whose direction happened to look approximately sunward because of how the spacecraft was oriented in space. To make progress, the team needed more data, much more data. And they needed older data, from the earliest years of Pioneer 10's mission, when the spacecraft had been in different parts of the solar system and the geometric ambiguity might have looked different. The problem was that those old tracking records weren't easily accessible. They had been written to magnetic tapes in the 1970s using formats that were no longer in common use. Many of the tapes had been sent to off-site storage and forgotten. Some had been damaged by humidity or magnetic fields. Recovering them would require dedicated funding, specialized equipment, and a team willing to spend years on what might turn out to be a fruitless treasure hunt. That funding came from an unexpected source. The Planetary Society, a non-profit space advocacy group co-founded decades earlier by Carl Sagan. The same Carl Sagan who had designed Pioneer 10's plaque took an interest in the investigation. The organization launched a crowdfunding campaign asking ordinary space enthusiasts to contribute toward the cost of recovering and digitizing the lost data. The response was enthusiastic. Donations poured in from around the world, from people who had grown up watching Pioneer 10's mission, from amateur astronomers, from teachers and students, and retired engineers. Funds enabled Turashev's team to track down old tape archives, restore aging hardware capable of reading them, and slowly bring decades of dormant tracking data back to life. The recovery effort itself became a story. Engineers built emulators that could decode obsolete data formats. Volunteers transferred recordings one by one onto modern storage media. Some tapes had been so badly degraded that only fragments could be salvaged. Others, miraculously, came back almost perfectly. As each new batch of historical data was added to the analysis, the picture of the anomaly grew sharper and more detailed. The effect had been there from the very beginning, ever since Pioneer 10 left the inner solar system. It hadn't been triggered by any particular event. It had simply been quietly present, a tiny constant pressure on the spacecraft, observable in retrospect once you knew to look for it. And the more data the team accumulated, the more the pattern began to suggest something specific, something almost embarrassingly close to home, something that pointed back, eventually, toward the spacecraft itself. By the mid-2000s, the investigation had reached a strange impasse. Years of theoretical work had produced no shortage of proposed explanations for the anomaly, but every one of them ran into problems. Modified Newtonian dynamics could account for the magnitude of the effect, but it had been developed to explain galaxy rotation, and applying it to spacecraft in the outer solar system required adjustments that began to feel uncomfortably ad hoc. Theories involving dark matter halos around the Sun had to invoke very specific distributions of unseen mass that conveniently produced exactly the right kind of pull. Cosmological explanations linking the anomaly to the Hubble expansion ran into difficulties when physicists worked out the detailed mathematics. Each beautiful idea, when poked hard enough, developed cracks. Each promising theory eventually disappointed the people trying to make it work. And while this was happening, the team analyzing the spacecraft data was uncovering its own quiet inconvenience. The anomaly might not be perfectly constant after all. The new finding emerged from the older recovered data. When Tarashev's group combined the recently digitized tracking records from the 1980s with the more precise measurements from the 1990s and early 2000s, they noticed something that hadn't been visible in the original analysis. The anomalous acceleration seemed to be slightly larger in the early years of the mission than in the later ones. The effect wasn't dramatic. The decline was small enough that it could easily have been a quirk of the older data, an artifact of the older tracking equipment, or a subtle systematic bias in how the historical records were being processed. But when the team checked it carefully, the trend held up. Over the course of 3 decades, the anomaly appeared to be very gradually weakening. Not by much, maybe a few percent over the whole span, but it was there, and it changed everything. A truly constant effect, a property of deep space, or of cosmic expansion, or of some new fundamental field, shouldn't change over time at all. Its value should be the same in 1980 as it was in 2002. The fact that the measurements suggested a slow decline pointed away from those kinds of explanations. It pointed instead towards something that itself was changing over time. Something connected to the spacecraft, perhaps, that was gradually wearing out, decaying, fading. And that opened up an explanation that had been lurking around the edges of the discussion for years, one that several physicists had quietly raised, but that had never been examined in the detail it deserved. Maybe the anomaly wasn't telling us something new about the universe. Maybe it was telling us something we had failed to model about the spacecraft itself. The idea was uncomfortable for a particular reason. It would mean that the most exciting physics result of the last 20 years, the experimental anomaly that had spawned hundreds of theoretical papers and inspired a whole generation of researchers to question the foundations of gravity, might turn out to have a thoroughly conventional explanation. It would mean that nature wasn't trying to teach humanity a new lesson about the cosmos. It would mean that humanity had been fooling itself. Many physicists, especially the ones who had invested years of work into novel theoretical models, did not want this to be true. They had begun to feel a certain affection for the anomaly. They wanted it to be real, to be deep, to be a window into physics nobody had ever glimpsed before. The notion that it might just be the spacecraft warming Earth's antennas with its own waste heat was almost insulting. But the thermal hypothesis kept coming up because it had one thing going for it that almost no other explanation did. It could naturally account for the slow decline. Pioneer 10 was powered by radioisotope generators, devices that produced electricity from the heat of decaying plutonium. That plutonium had a half-life of about 87 years, which meant that every year the amount of heat the generators produced decreased by a small but predictable amount. If the anomaly was somehow being produced by heat emitted from the spacecraft, then as the heat output decreased, the anomaly should weaken in roughly the same proportion. And the rate of decrease that the data seemed to show was, suspiciously, in the right ballpark for plutonium decay. The problem was actually proving it. To turn the thermal hypothesis from a vague intuition into a testable explanation, you needed to do something nobody had previously attempted. You needed to model, in painstaking detail, every source of heat on Pioneer 10. The plutonium generators themselves, the electronics inside the main equipment compartment, the small heaters that kept various components from freezing in deep space, every wire and circuit and panel that converted electrical energy into waste heat. You needed to know exactly how that heat was distributed across the spacecraft's surface and exactly how it radiated away into space. Because heat, when it leaves an object, carries momentum. It is a form of light, and if more heat radiates out of one side of the spacecraft than the other, that asymmetry produces a tiny force, a thermal recoil, pushing the spacecraft in the direction opposite to where the heat is escaping. For a normal spacecraft, this effect is small enough that it can usually be ignored. But Pioneer 10 wasn't a normal spacecraft. It had been built in an era before detailed thermal modeling was standard practice. Its radioisotope generators were mounted on long booms extending away from the main body. Its high-gain antenna was a large dish that radiated waste heat preferentially in certain directions. The geometry of the spacecraft, simple as it looked from the outside, produced a complicated three-dimensional pattern of thermal emission. To compute the resulting recoil force, you needed engineering drawings, material specifications, thermal properties of every surface, and computational tools sophisticated enough to model how infrared radiation flowed out from each part of the spacecraft into the cold vacuum surrounding it. This kind of analysis was vastly more difficult than it sounded. Pioneer 10 had been designed in the late 1960s and built in the early 1970s. Many of the original engineers had retired or died. The detailed thermal documents from the construction era were scattered across various archives, some at JPL, some at TRW, some lost entirely. Even when you could find the documents, translating them into a modern computational model was a project unto itself. For years, nobody had the time or the funding to do it properly. Quick estimates suggested that thermal recoil could account for some of the anomaly, but probably not all of it. Those estimates were tentative, based on rough assumptions, and the physicists hopping for new fundamental physics could comfortably dismiss them. The thermal explanation lingered in the background, plausible but unproven, frustrating to everyone who wanted a definitive answer. Meanwhile, Pioneer 10 itself was running out of time. The decline of its power source meant that the spacecraft was producing less and less electricity each year. Its transmitter was growing weaker, its instruments were going dark one by one, and the signals reaching Earth were becoming so faint that even the Deep Space Network was struggling to detect them. In April 2002, mission controllers received what would turn out to be the last full data transmission from the probe. In January 2003, they picked up one final, barely audible chirp from the spacecraft, more than 7 billion miles away. After that, nothing. The little machine that had carried humanity's first message into interstellar space had finally fallen silent, leaving behind a mystery that the people who built it had never been able to solve. The man who finally solved the Pioneer mystery was the same man who had spent more than a decade refusing to accept any easy answer to it. Slava Turyshev had heard the thermal hypothesis from his colleagues 100 times by 2007. He had nodded politely each time, acknowledged that it might be part of the story, and gone back to his own work. He had personally written papers exploring exotic explanations for the anomaly, dabbled in modified gravity theories, considered cosmological connections. He was a theorist by training, drawn to the elegant possibility that the pioneers had stumbled onto something deep. But he was also a meticulous scientist, and meticulous scientists eventually have to confront the data even when the data tells them something boring. By the late 2000s, Turyshev had decided that he was going to do the thermal calculation properly, not the rough estimates everyone had been arguing about for years. The real thing, the one that nobody had done because it would take years of work and might prove the entire anomaly had been a glorified accounting error. He assembled a small team and began what would become one of the most exhaustive engineering reconstructions ever attempted on a long-dead spacecraft. They tracked down the original Pioneer 10 blueprints from TRW's archives, some of them stored on yellowing paper that had to be carefully scanned before it disintegrated. They located thermal test data from the early 1970s, performed when the spacecraft was being qualified for flight. They interviewed retired engineers who could still remember design decisions made 40 years earlier, men in their 70s and 80s who had spent their careers building machines for other worlds and were astonished to receive phone calls about a project they had assumed nobody cared about anymore. Slowly, painfully, the team rebuilt a digital model of Pioneer 10 from the inside out. Every panel, every component, every surface that radiated heat into space. Every internal pathway through which warmth flowed from the plutonium generators outward toward the void. The model that emerged was extraordinarily complex. Pioneer 10 had not been designed as a thermally symmetric object. It had been designed to do a job, and the job had imposed certain geometric constraints that, decades later, would turn out to be exactly the wrong constraints if you wanted heat to leave the spacecraft evenly in all directions. The radioisotope generators, the main sources of heat, were mounted on long booms extending out to the sides. That arrangement had been chosen so that their radiation wouldn't damage the sensitive scientific instruments mounted closer to the spacecraft body. But it also meant that the heat from those generators tended to radiate primarily in directions perpendicular to the spacecraft's spin axis, not equally toward the front and back. Meanwhile, the back of the high-gain antenna dish acted like a kind of reflector, bouncing infrared radiation from the spacecraft's interior in particular directions. The cumulative effect was that more thermal energy escaped from the spacecraft in one direction than another, and the direction with the larger emission happened to point away from the sun, which meant the recoil from that radiation gave Pioneer 10 a tiny continuous push back toward the sun. When the team plugged numbers into their model, they held their breath. They had spent years building it. They had no idea what it would say. Either it would predict a thermal recoil force comparable to the observed anomaly, in which case the mystery was solved, or it would predict something much smaller, in which case the anomaly would remain stubbornly unexplained, and the field would be back where it had been a decade earlier. The first complete simulations came back in 2010. The predicted thermal force was large, not just a small contribution to the anomaly, a force that could account for most of it, and perhaps all of it, within the considerable uncertainties of the modeling. Tarashev refined the calculations, tested different assumptions, ran the numbers 100 different ways. The conclusion held up. The Pioneer anomaly, the great unsolved mystery of deep space physics, the puzzle that had spawned hundreds of theoretical papers and inspired a generation of researchers to question the foundations of gravity, was the spacecraft's own waste heat pushing gently against itself for decades. The paper announcing this conclusion was published in 2012 in Physical Review Letters, the same journal that had carried the original 1998 announcement. The new title was almost the mirror image of the old one: Support for the Thermal Origin of the Pioneer Anomaly. The contrast couldn't have been clearer. What had been an indication of an apparent anomalous acceleration was now being explained by the mundane physics of infrared radiation from a 30-year-old spacecraft. The reaction in the physics community was a complicated mixture of feelings. There was relief, because the conventional framework had been vindicated. There was disappointment, because the dream of new physics had been deflated. There was respect, because the analysis had been done so carefully and so thoroughly that even die-hard skeptics found it hard to dismiss. And there was a kind of quiet awe at the realization that the universe, in the end, had not been trying to whisper a secret. The spacecraft had been doing it to itself, in plain sight, for the entire mission, and nobody had thought to model it carefully enough to notice. This was the moment that reframed everything, because the Pioneer story, when you stepped back and looked at it from the perspective of 2012, wasn't really a story about a flaw in the laws of physics. It was a story about how humans do science, about how a tiny discrepancy can grow into a global investigation, how confirmation bias can pull people toward exotic explanations, how decades of careful work can be required to rule out the simple answer that was sitting right there the whole time. The anomaly had taught the physics community a lesson, but not the lesson everyone had originally hoped for. It had taught them about humility, about how easy it is to miss a piece of basic engineering when you are dreaming of new fundamental laws, about how the universe sometimes refuses to be exotic, even when we very badly want it to be. But there was also something else, something that the official papers couldn't quite capture: The resolution of the Pioneer anomaly had a strange poetic quality to it. The spacecraft, more than 7 billion miles from home, had been quietly slowing itself down with its own dying heat. The plutonium that powered it had been gradually decaying for 30 years, growing colder, fading toward eventual silence. As it had faded, the anomaly had faded with it, both expressions of the same slow exhaustion. When Pioneer 10 finally went dark in 2003, it wasn't just a transmitter falling silent. It was the source of the anomaly itself burning out. The mystery and the spacecraft had been the same thing all along, and they had died together. Carl Sagan's plaque, etched with the figures of a man and a woman and a map of where the spacecraft had come from, would continue traveling forever through interstellar space. But the strange acceleration that had haunted the spacecraft for its entire active life was over. The heat that had pushed it was gone. Pioneer 10 was finally, truly, at the mercy of nothing but gravity and inertia, drifting at a constant velocity through a darkness it would never illuminate again. The resolution of the Pioneer anomaly produced ripples through physics that went in directions almost nobody had anticipated. The most obvious change was the one nobody wanted to talk about. For nearly 15 years, a substantial part of the theoretical physics community had been writing papers, applying for grants, attending conferences, and building careers partly around the possibility that the Pioneer effect was a window into new fundamental physics. When the thermal explanation took hold, all of that work didn't quite become wrong, but it certainly became harder to motivate. Researchers who had spent years arguing that the anomaly might be evidence for modifications to gravity or signatures of dark matter or hints of extra dimensions suddenly found themselves needing to reframe their work. The papers didn't get retracted, exactly. They just got quietly cited less often. The conferences moved on to other topics. The next generation of graduate students started choosing different dissertation problems. This was a healthy correction, even if it strung, because what the Pioneer saga had exposed was a tendency in physics that the community had been only dimly aware of before. The willingness to entertain exotic explanations had outpaced the willingness to do the boring engineering work of ruling out conventional ones. That asymmetry hadn't been intentional. It was a natural consequence of how the field operated. Exotic theories were exciting. They got published in prestigious journals. They attracted media attention. They produced collaborations and funding. Doing detailed thermal modeling of a 30-year-old spacecraft, by contrast, was tedious, expensive, slow, and unlikely to generate any glamorous result. The reward structure of the field had pulled everyone in the wrong direction, and only a few stubborn researchers like Turyshev had been willing to spend years doing the unglamorous work that turned out to be the real answer. After Pioneer, conversations about methodology in the physics community took on a slightly different tone. People talked more about the importance of doing the dull calculations first, of always asking whether a mundane explanation had been properly ruled out before reaching for an extraordinary one. The implications for spacecraft engineering and mission planning were even more direct. Every probe NASA had launched between Pioneer 10 and the late 2000s had been tracked using software that didn't include detailed thermal recall modeling. For most of those missions, the effect was small enough not to matter. For some, like Galileo and Ulysses, similar small anomalies in the tracking data had been quietly noted and never resolved. Now mission engineers had a clear understanding that thermal forces were real, predictable, and potentially significant for any precision navigation problem. New tools were developed for incorporating thermal modeling into trajectory calculations from the beginning of a mission, rather than as an afterthought. Computer-aided design software for spacecraft began including thermal recall simulations as a standard feature. When New Horizons was sent toward Pluto, when the Juno probe was sent to Jupiter, when more recent missions like Lucy and Psyche were designed for journeys to the asteroid belt, all of them were modeled with a level of thermal detail that simply didn't exist when the Pioneers were built. The little anomaly that had haunted physics for 2 decades had quietly forced an entire engineering field to grow up. There was a more subtle effect on general relativity itself. Einstein's theory of gravity had been considered one of the most well-tested ideas in science for a long time. But the Pioneer anomaly had raised the uncomfortable possibility that the theory might have been falling apart at scales beyond the orbit of Neptune, in regions where it had never been precisely tested. When the thermal explanation closed that possibility, general relativity emerged from the episode with its credibility not just intact but strengthened. The careful resolution of the anomaly had effectively demonstrated that within the outer solar system, gravity behaved exactly the way Einstein had said it would, all the way out to distances where humanity had never directly verified the equations before. This was actually a major scientific result. It meant that future missions to the deepest parts of the solar system could rely on standard physics without worrying about small, unexplained corrections. It meant that proposals to send spacecraft to study the outermost reaches of the heliosphere, the boundary where the sun's influence gives way to interstellar space, could be planned with confidence in the navigation tools. For the theories that had been built up to explain the anomaly, the consequences were more complex. Modified Newtonian dynamics, which had briefly enjoyed a surge of attention because its predictions seemed to fit the Pioneer numbers, didn't disappear. The theory still had its motivating problem, the rotation of galaxies, which dark matter explained somewhat awkwardly. But the loss of Pioneer as supporting evidence weakened MOND's position considerably. Without that local solar system observation, the theory was once again restricted to making predictions about distant galaxies, predictions that were harder to test and easier for skeptics to ignore. The theorists who had built careers around MOND continued their work, but the broader physics community drifted back toward the standard dark matter framework, content to wait for direct laboratory detection rather than fundamental modifications to gravity. The story was similar for some of the more exotic proposals. Theories invoking extra dimensions or cosmological connections to local accelerations had to retreat to their original motivations and find other observational hooks. The Pioneer data was no longer available as ammunition. There was something philosophically important about how the resolution played out. Throughout the entire investigation, the physics community had been confronting a tension between the appeal of new ideas and the discipline of conventional science. Different researchers had taken different sides. Some had been openly hopeful that new physics would emerge. Others had been openly skeptical, insisting from the beginning that some boring explanation would eventually surface. When the thermal model finally settled the question, neither camp got exactly what they wanted. The hopeful researchers had to accept that their excitement had been misplaced. The skeptical researchers got to be right, but only after 15 years of insisting that the answer would be conventional without doing the work to prove it. The credit, in the end, belonged to the people who hadn't taken a side, who had simply done the hard work of ruling out one explanation after another until only one remained standing. Slava Turyshev, John Anderson, the engineers at JPL who had patiently reconstructed Pioneer 10's thermal properties from 40-year-old drawings, these were the people the story really belonged to. And there was one final ripple, one that wouldn't fully play out for years. The Pioneer investigation had set a precedent. When the next deep space anomaly appeared, when some future spacecraft started showing some new unexplained behavior in its tracking data, the physics community would now know how to respond. It would know to take the data seriously without rushing to invent new physics. It would know to verify every conventional explanation before reaching for an exotic one. It would know to be patient, to do the engineering work, to keep its excitement in check until the simpler answers had all been ruled out. The Pioneer anomaly hadn't given us new physics, but it had given us something else. A model for how to investigate the next mystery, whatever it turned out to be. And in a field as cautious and slow-moving as deep space science, that lesson was worth all the years of struggle it had taken to learn. There is a particular kind of feeling that comes from realizing you've sent something into the universe that will outlive everyone you have ever known. Pioneer 10 carries that feeling on board, etched into a small gold plaque bolted to its antenna struts, and the meaning of that plaque grows stranger and more poignant the longer you think about it. The spacecraft is currently moving through the constellation Taurus, heading roughly in the direction of the star Aldebaran. It will take Pioneer 10 about 2 million years to reach Aldebaran's general vicinity, by which time the star will have moved and Pioneer will pass through empty space where it once was. After that, the probe will keep traveling, tens of millions of years, hundreds of millions of years, through galactic time scales that make human history look like a single flickering instant. And the plaque, in all that time, will not significantly degrade. Interstellar space is too empty to erode it. The probe is, for all practical purposes, eternal. That permanence sits inside the Pioneer story in a quiet way that most people never quite let themselves feel. Every human who watched Pioneer 10 launch from Cape Canaveral in 1972 is now either elderly or deceased. The engineers who built it, the scientists who designed its mission, the journalists who covered it, the children who pressed their faces against television screens to watch the rocket lift off, all of them have moved on, generation by generation, and the probe has kept going. There is no force in the universe likely to stop it. No planet stands in its way. No star will pass close enough to alter its trajectory significantly. Even when humanity itself is gone, when our species has either left the planet or been replaced by something else or quietly vanished into the long darkness, Pioneer 10 will still be out there, still drifting at 26,000 miles per hour, still carrying its little aluminum greeting card to whoever might one day find it. The investigation into the anomaly took 30 years. The probe's journey will take billions. This is why the Pioneer story matters in a way that goes beyond physics. The spacecraft was a piece of the species reaching outward, not a particularly fancy piece, not a billion-dollar flagship mission. A modest, almost humble little machine built on a tight budget by engineers who didn't expect it to do half of what it ended up doing. And yet, because of how the laws of motion happen to work in our universe, that humble little machine became the longest-lasting artifact our civilization has ever produced. Pyramids erode, cities crumble, monuments wear away. Even the radio signals that humanity has been broadcasting outward since the early 20th century will eventually dissipate into noise, indistinguishable from the cosmic background. But Pioneer 10 will keep going. The plaque will keep saying what it has always said. Look, we were here, we did this. We came from a small blue planet near a small yellow star, and at one particular moment in our history, we managed to build something that could leave. The fact that the anomaly turned out to be ordinary doesn't diminish this. If anything, it intensifies it, because the resolution of the mystery revealed something about how humans actually behave when faced with the unknown. We chase, we persist. We refuse to let small puzzles go even when the rest of the world has moved on. John Anderson noticed a tiny discrepancy in tracking data in the early 1980s and spent the next 3 decades of his career on it. Slava Turyshev came from another country, joined the investigation, and gave years of his own life to chasing a number that almost everyone thought would never be solved. The Planetary Society, an organization of ordinary citizens who care about space, raised money to recover old magnetic tapes that had been gathering dust in storage rooms. Engineers in their 70s got phone calls about machines they had built decades earlier and willingly spent their retirement years reconstructing forgotten thermal designs. None of these people had to do any of this. Pioneer 10 was already gone. The anomaly affected nobody's daily life. And yet somehow the puzzle got solved because humans, given enough time, eventually solve the puzzles they care about. That stubbornness is one of the few things that genuinely sets our species apart. Most of what we do, other animals do too. We build shelters. We hunt and gather. We form social bonds. We communicate. But the long, patient, multi-generational pursuit of small mysteries that have no practical importance, this is a behavior that, as far as we can tell, only humans engage in. A bird does not spend 3 decades wondering why a leaf falls in a particular pattern. A wolf does not assemble a research team to investigate an unexpected echo. Only humans care enough about understanding the world to keep working on problems long after the original investigators have died, retired, or given up. The Pioneer story is a perfect example of that strange compulsion in action. A probe traveling silently through the dark, a tracking discrepancy of a few hundred meters per year, a question that nobody needed answered, and yet a global community of researchers spent careers chasing it anyway. There is also something to be said about what the Pioneer story means for our relationship with the cosmos. For a long time, the anomaly held out the promise that nature was trying to tell us something, that there was a secret in the data, a hidden truth waiting to be revealed. When the truth turned out to be thermal recall, that romantic interpretation had to be set aside. But in its place came something quieter and perhaps more honest. The universe doesn't always whisper secrets. Sometimes it just is what it is. Gravity works the way Einstein said. Heat radiates from spacecraft according to known physics. Plutonium decays at its predicted rate. The cosmos isn't trying to teach us anything. We are trying to learn from it, and the difference between those two framings matters. The Pioneer story is a reminder that we are the active party in this relationship. We are the ones asking questions, building instruments, doing analysis, trying to understand. The universe is just being itself. The understanding comes from us. And then there is the simple human pleasure of knowing that something we made is out there. The next time you walk outside on a clear night and look up at the sky, somewhere out there, in the rough direction of Taurus, a little machine you have never seen is drifting through the void at 26,000 miles per hour. It cannot send signals anymore. Its plutonium is nearly spent. Its instruments are dark, but it exists. It still moves. And the plaque on its side still says what Carl Sagan and Frank Drake and Linda Saltzman Sagan asked it to say all those years ago. That we existed, that we tried to reach out, that at this particular point in the long story of our species, we built a machine and sent it on the longest journey any human-made object has ever taken, and we waved goodbye, and we never forgot it. The resolution of the Pioneer anomaly didn't end deep space mystery investigation. It just shifted the focus. There are still spacecraft out there showing small unexplained behaviors that haven't been fully accounted for, still questions about how matter, light, and gravity behave at the edges of the solar system, still puzzles that the next generation of researchers will inherit. The flyby anomaly, the strange small velocity changes that some spacecraft picked up when swinging past Earth, remains one of the more uncomfortable loose ends. Unlike the Pioneer effect, it hasn't been linked to thermal recall or any other definitive explanation. The deviations are too brief to allow the kind of long baseline analysis that finally solved the Pioneer mystery. Some recent flybys have shown anomalies, others have not. The pattern, if there is one, has been frustratingly difficult to characterize. Researchers continue to monitor every Earth swingby, but progress is slow, and the answer, when it finally comes, might require another 2 or 3 decades of patient observation. Then there are the Voyagers. Pioneer 10 had a pair of younger siblings, Voyager 1 and Voyager 2, which were launched in 1977, 5 years after the Pioneers, and which carried more sophisticated instruments and more powerful transmitters. The Voyagers conducted the famous grand tour of the outer solar system, visiting Jupiter, Saturn, Uranus, and Neptune over the course of more than a decade, sending back the iconic images that defined humanity's first close look at the outer worlds. And after their planetary work was finished, both Voyagers continued outward, following trajectories that would eventually carry them beyond the heliosphere into interstellar space. In 2012, Voyager 1 became the first human-made object to leave the bubble of solar wind that surrounds our star, entering a region of space where the dominant influences come not from the Sun, but from the wider galaxy. Voyager 2 followed in 2018. Both spacecraft are still operating, more than 40 years after launch, and both are continuously transmitting data back to Earth from distances that dwarf anything Pioneer 10 ever reached. The Voyagers are now in the territory that Pioneer was heading toward when its signal finally faded, and their tracking data, scrutinized in the wake of the Pioneer anomaly's resolution, has been processed with much more sophisticated thermal models from the start. So far, neither Voyager has shown an unexplained acceleration that resembles the Pioneer effect. This is both reassuring and slightly disappointing. Reassuring because it suggests that the thermal explanation really did capture the essential physics. Disappointing, because it means there isn't a fresh anomaly to chase in the latest data. The Voyagers continue to surprise scientists with their measurements of the interstellar magnetic field, the density of plasma beyond the heliopause, the texture of cosmic radiation in regions where no probe has ever traveled before. But they aren't showing the kind of mysterious gravitational behavior that defined the Pioneer story. Their batteries are dwindling. Their instruments are being shut down one by one to conserve power. Within a few more years, the Voyagers, like the Pioneers before them, will fall silent forever, and humanity will have to choose whether to send something else or to let the deep space frontier go quiet until the technology and the budget align again. A small but determined group of researchers is pushing for new missions explicitly designed to test gravity and motion in the outer solar system. The most ambitious of these is the Interstellar Probe concept, currently in early study at NASA. The proposed spacecraft would be launched on a powerful upper stage, possibly with a slingshot through the sun's gravity to gain unprecedented speed, with a goal of reaching 1,000 astronomical units, more than 30 times Pluto's distance, within a single human career. Along the way, it would conduct precision tracking experiments specifically designed to look for any deviations from standard physics, with thermal modeling built in from day one to avoid the kind of confusion that haunted the Pioneer investigation. The mission is years away from approval and decades away from launch. But if it flies, it will be the most ambitious test of gravity in the outer solar system ever attempted, with measurement precision orders of magnitude beyond anything Pioneer 10 could achieve. There are also proposals to use the sun itself as a gravitational lens. Einstein's general relativity predicts that the gravity of the sun bends light passing near it, and at a distance of about 550 astronomical units, the bent light from distant objects converges into a focal region. A spacecraft positioned there could use the sun as a natural telescope, gathering images of exoplanets with resolution far beyond anything that could be achieved with conventional instruments. Reaching that focal region requires the same kind of technology that an interstellar probe would need, and the journey would take decades. But the scientific payoff would be extraordinary. We could potentially see continents and oceans on planets light years away, study their atmospheres in detail, look for signs of life or civilization. The pioneer-era engineering that made deep space exploration possible would be enabling the gravitational lens mission as well, even if the spacecraft itself would be far more sophisticated than anything humanity has yet built. Closer to home, a new generation of gravity testing missions is being planned. The European Space Agency's LISA project, the Laser Interferometer Space Antenna, will launch in the 2030s and will use 3 spacecraft flying in a precise triangular formation to detect gravitational waves with unprecedented sensitivity. While not directly related to the Pioneer mystery, LISA represents the same impulse to push our understanding of gravity into regimes where it has never been precisely tested. The mission will require the kind of thermal modeling and trajectory analysis that the Pioneer investigation helped develop. The lessons learned from chasing that tiny anomaly for 30 years are now embedded in the design of one of the most ambitious physics experiments ever attempted. And there are still questions about Pioneer 10 itself. The last signal was received in 2003, but the spacecraft is presumably still out there, still drifting outward, still carrying its plaque toward a star it will never quite reach. We have no way to confirm its current position. Without an active transmitter, the probe is essentially invisible to us. We know roughly where it should be based on extrapolating its trajectory forward in time, but the actual location can no longer be measured. In some sense, this is poetic. Pioneer 10 spent its active life being tracked with extraordinary precision, the small deviations from its predicted path triggering decades of investigation. Now it travels in true freedom, unobserved, unmonitored, drifting through space with no one watching where it goes. The most studied trajectory in human history has become, in death, completely untracked. Researchers occasionally talk about whether some future mission might attempt to catch up with one of the Pioneers or Voyagers and study them up close. The engineering challenges are formidable. The probes are moving fast and have been drifting for a long time, which means any catch-up mission would need to launch at a significantly higher speed and travel for a very long time before rendezvous. But the idea is not entirely fantasy. As propulsion technology improves, as humanity's interstellar ambitions grow, there is a non-zero chance that someone, someday, will design a mission specifically to find one of these old probes and bring back the plaque, or at least photograph it where it floats. That mission, if it ever happens, will be a kind of cosmic homecoming, a meeting of our descendants with the ancestor spacecraft we sent into the dark. There is a particular kind of silence that exists nowhere on Earth. Even in the deepest deserts, in the quietest forests, even at the bottom of the ocean, there is always something. The whisper of wind, the hum of distant water, the faint rustle of life going about its business. But out where Pioneer 10 drifts, more than 7 billion miles from the sun, and growing more isolated with every passing second, there is nothing. No air to carry sound, no molecules to vibrate, no life within unimaginable distances. The little probe moves through a darkness so absolute that the human imagination struggles to hold it. Even the stars, those familiar beacons that fill our night skies on Earth, appear out there only as distant points scattered across an emptiness that goes on without end. To think about Pioneer 10's environment is to confront a scale of solitude that has no analogue in human experience. And yet, somehow, that solitude is what we sent it into. We built something specifically to occupy a kind of loneliness that none of us could ever survive. What Pioneer 10 did, in the end, was extend the reach of human consciousness into a region of the universe that no consciousness had ever touched before. For 4 billion years, the outer solar system had existed without ever being observed by a thinking being. Jupiter's clouds had churned in their patterns, Saturn's rings had circled in their delicate orbits, the cold rocks of the Kuiper belt had drifted in their slow, lonely loops, all of it happening without any audience, without anyone to notice or care that it was happening at all. Then, in a few brief years in the 1970s, a small machine with a single antenna and a handful of cameras moved through that previously unwatched territory and started telling Earth what was there. The information traveled back as faint radio whispers, was caught by the great dishes of the Deep Space Network, was decoded into images and numbers, and was eventually projected onto the screens of scientists who looked at them and saw, for the first time in the history of the universe, what the outer planets actually looked like up close. This is not a small thing. This is the consciousness of one species briefly illuminating regions of reality that had been dark in every meaningful sense for the entire previous existence of the cosmos. The strange beauty of the Pioneer story is that this immense act of cosmic illumination happened almost casually. There were no fanfares. No statues were built to commemorate the moments when humanity's awareness first reached past Jupiter, past Saturn, past Neptune. The spacecraft was, in its time, just one of many missions, and many of the people who worked on it have probably never been thanked by name in any meaningful public way. And yet the consequences of what they did will outlast every civilization their species ever builds. Pioneer 10's plaque will still be drifting through space when the sun has expanded into a red giant and burned away the surface of the Earth. When the galaxy itself has merged with Andromeda and rearranged its stars into new configurations. When trillions of years of cosmic time have passed and the universe has grown dim and cold beyond anything we can currently imagine. The probe is, in a real sense, a contribution to the universe that will be present long after we ourselves are gone. This puts the anomaly investigation into a slightly different perspective. For 3 decades, brilliant scientists labored over a tracking discrepancy involving a spacecraft that, in the cosmic scheme of things, was barely past the front porch of our own neighborhood. The numbers they were chasing represented motion changes so small that they would never affect any practical concern, never alter any human life, never change anything that any reasonable person would call important. And yet the chase was important anyway, because we were the ones doing it. The investigation was an expression of a particular feature of consciousness that the universe seems to have produced exactly once, on at least one small planet near a quiet star. The feature of being curious about things that don't need to be cared about, of refusing to accept "I don't know" as a permanent state, of dedicating years and decades of finite life to puzzles whose only reward is the puzzle being solved. Whatever else the pioneer story is, it is a demonstration of this peculiar human refusal to leave questions alone. The cosmic perspective that emerges from contemplating Pioneer 10 has a particular flavor. It is not the perspective that says we are insignificant. That framing has always struck me as a bit lazy, a too easy conclusion from looking at large numbers. We may be small in the spatial sense, our planet a speck near an undistinguished star, in an unremarkable galaxy, in a universe full of trillions of galaxies. But spatial size is a strange thing to measure ourselves by. The universe contains many things larger than us, but as far as we can tell, it contains almost nothing capable of measuring itself the way we measure ourselves. Most of the matter in the cosmos has no idea it exists. The vast galaxies and clusters and superclusters are just patterns of particles obeying physical laws, with no internal experience of their own grandeur. Whatever it is that humans are doing when we contemplate the universe is not doing it back. The asymmetry is striking. We are, by every measure that distinguishes consciousness from raw existence, doing something the rest of reality is not doing. The Pioneer probe traveled into emptiness, but it carried with it a small piece of a process that empties places themselves cannot perform. It carried a fragment of the cosmos's capacity to know itself. This is what the plaque is really for when you think about it carefully. Not to greet aliens, although that's the surface explanation. The plaque is a declaration. It says, somewhere in this universe, there exists at least one species that thought to make a map of where it came from, etch it onto metal, bolt it to a spacecraft, and send it into the dark. It says, whatever else may be true of the cosmos, there is at least one place where matter has organized itself to such a degree that it can build representations of itself and launch them out beyond its own world. The plaque is humanity's evidence, attached to a vehicle traveling forever. And the entire decades-long investigation into the Pioneer anomaly was just another version of the same gesture, a demonstration that we cared, that we noticed, that we paid attention. The investigators didn't just track a spacecraft. They affirmed, through the very act of pursuing the mystery, that conscious beings continue to be present in this universe, asking questions, refusing easy answers, looking out into the dark with their tools and their instruments and their stubborn unwillingness to stop. The probe is a kind of proof of our existence. The investigation was another kind. Both will, in their own ways, outlast us. Somewhere out beyond the boundary of the heliosphere, in a darkness that no human eye will ever see directly, Pioneer 10 is still moving. It has been moving since 1972, and it will continue to move long after every person alive today has died, long after the cities we live in have crumbled, long after the languages we speak have evolved into something unrecognizable. The probe doesn't know any of this. It hasn't known anything for over 20 years now, since its final whisper reached Earth in January 2003, and its transmitter went quiet for good. It is a dead machine traveling through a dead region of space, and yet every time anyone tells the story of how it got there, of what it did, of what it taught us, of how it managed to fool a generation of physicists into thinking they had found the edge of known reality, the little probe comes briefly back to life inside the minds of the people listening. That is its strange afterlife. It exists in our remembering of it, more vividly now than it ever did when it was actually transmitting data. The mystery it carried with it for 3 decades turned out to be its own warmth pushing it gently backward, an embarrassing answer in some ways, but also a deeply intimate one. The spacecraft was, in the end, slowed by itself. The plutonium inside it had been generating heat all along, that heat had been escaping into space asymmetrically, and the recoil from that escape had been pulling on the probe like a soft hand on a runaway kite. When you understand it that way, the anomaly stops being an exotic cosmic puzzle and becomes something more poignant. Pioneer 10 was being held back by the same energy source that kept its instruments alive. The thing that powered it was also the thing that resisted its journey. Every watt of electricity its plutonium produced was, in some small fraction, working against its own escape. And the moment the plutonium ran out, the anomaly ran out with it. The probe became, finally, a perfect inertial body, drifting forever at whatever velocity it happened to have at the moment its heat ran cold. There is something almost human in that arrangement. We too are slowed by the very things that animate us. Our ambitions, our attachments, our weights of memory, all of them pulling against the trajectories we imagine for ourselves. We carry our anomalies with us, the small forces we never quite manage to model accurately, until eventually those forces fade and something else takes over. Pioneer 10 was a machine, but in its long, quiet behavior, it accidentally produced a metaphor that nobody designed it to produce. A metaphor about how things move through the universe, about how the substances that power us also slow us, about how, in the end, we drift on the momentum of what we did when we were still warm. The investigation that took place around that drifting machine was, in its own way, the more important story. Not because the answer turned out to be groundbreaking, but because the chase revealed something about how science works at its best. A small discrepancy in tracking data was noticed by one physicist. He told some colleagues. They told other colleagues. Years passed. Independent software was written. Old tapes were dug out of storage. A non-profit organization raised money from ordinary people who cared about the answer. Engineers in retirement came back to consult on machines they had built in their youth. Theorists around the world proposed exotic ideas, most of which turned out to be wrong, but all of which contributed to a slow communal narrowing of possibilities. And eventually, after more than 30 years of patient work by people who had every reason to give up, the answer emerged. Quietly, mostly without celebration. Not the answer anyone had hoped for, but the answer that was true. That is the shape of science when it functions properly. It is slow. It is collaborative. It accepts boring conclusions. It values the truth more than the spectacle. The story is also a reminder that the universe, while inexhaustibly interesting, is not actively trying to dazzle us. It is just being itself. The sun pulls on its planets the way Einstein's equations describe. Heat radiates from objects the way thermodynamics demands. Spacecraft drift through empty space according to laws we understand. There are no secret messages embedded in deep space tracking data. There is just deep space and tracking data and the human minds working to bridge the gap between them. And those human minds, contrary to almost every cliché about how small and lost we are in the cosmos, turn out to be remarkably capable of figuring things out. We figured out the orbits of the planets. We figured out the structure of atoms. We figured out gravity, at least to the precision that matters at every scale we have so far tested. And we figured out the Pioneer anomaly, even though it took decades of patient labor across multiple generations of researchers. The universe doesn't yield its secrets easily, but it does yield them, given enough time and stubbornness. Pioneer 10 is now beyond reach. We cannot see it. We cannot send it new instructions. We cannot recover it. It is part of the cosmos in a way that we ourselves are not, fully committed to a journey from which there is no return. But the act of having sent it has changed something about our species. We are now a civilization that has placed objects beyond the planets. We are a people who have built things that will outlast us by timescales that make our own existence look momentary. We have crossed a threshold that before 1972, no species on this planet had ever crossed. And somewhere on that little probe, on a small gold anodized plaque, the figures of a man and a woman stand quietly, holding up their hands, declaring the existence of a place called Earth and a species called humanity. The plaque will keep saying that for as long as anything in the universe can be said to be saying anything. Forever, by the only measure that matters. If this story moved you the way it moves me, if you find yourself looking up at the night sky tonight and wondering what else is out there waiting to be understood, please take a moment to like this video and subscribe to the channel. It really does make a difference. It helps these stories find the curious minds that want to hear them. If you have thoughts about Pioneer 10, about the anomaly, about the team of researchers who chased the answer for 30 years, Share them in the comments. I read everything, and the conversations that happen below these videos are some of the best parts of doing this work. And if you know someone who would love this story, someone who looks up at the stars and feels what you feel when you look at them, please pass this along. Stories like this one deserve to be heard by everyone who would care. Pioneer 10 is still out there, drifting toward Aldebaran, carrying its small message into the long dark. Whatever else may happen to our species, however bright or short our future turns out to be, we did this. We sent it, and it is still going. Good night, and keep looking up.